By now we understand that the brightness or the radiance of a point in the scene has something to do with its material properties or its reflectance properties. And so we want to come up with a concise way of representing the reflectance properties of any material out there in the scene. And that brings us to the bidirectional reflectance distribution function, or BRDF. But let's take a look at first how material properties drive appearance. Here's a bunch of spheres in the scene which are rendered, and the illumination in this case is very distant. So irrespective of how complex the illumination is, every sphere here is essentially seeing the same illumination. And also the spheres are being observed by a camera that is really far away. So the viewing direction for every sphere is also the same. So the only reason that these spheres look different from each other is because they're made of different stuff, different materials, and therefore they have different reflectance properties. They have different abilities to take light from a direction and reflect it in a different direction. So that brings us to surface reflectance. We see that there are two directions that are important to us. One is the direction from which the light arrives, and the second is the direction in which light is being reflected and observed. So to represent the reflectance properties of any material, we want to be able to describe its properties both in terms of the illumination direction and the viewing direction or the reflection direction. So that brings us to the bidirectional reflectance distribution function. Bidirection because of these two directions that are important to us. So how do we describe direction? We can do it using two angles, theta, which is the zenith angle, and phi, which is the azimuthal angle, which lies on the xy plane. So we can say that the direction of the light source, the direction from which the light arrives, is theta I phi I. I is for incidence. And the direction in which the light is being reflected is theta r phi r, where r is for the direct reflection. So we can say that the irradiance of the surface due to a source in the direction theta I phi I is E theta I phi I. And the radiance of the surface in the direction theta r phi r is L theta r phi r. And now we describe the reflectance, the bidirectional reflectance distribution function, BRDF, of the surface as the ratio of L to E. The radiance in the direction theta r phi r due to the irradiance from the direction theta I phi I. And therefore it's a four-dimensional function. We have theta I, phi I, theta r, phi r. So this function f fully describes the reflectance properties of any point in the scene. And the units are 1/steradian. So let's take a look at some of the properties of BRDF. The first property is that it must be greater than 0. We know that the irradiance cannot be negative. We know that the radiance cannot be negative. We can't reflect negative light energy, and therefore f is greater than 0. More interesting is the Helmholtz reciprocity, which simply says that you can flip the illumination direction and the reflectance direction, and you get the same BRDF. So in other words, if you flip the camera and the light source, as far as the surface is concerned, it has the same BRDF. It doesn't mean that the camera is going to observe the same brightness in both these configurations. It simply means that the ability of the surface to take light from one direction and put it out in the other direction is the same as its ability to take light from the second direction and put it out in the first direction. So that's Helmholtz reciprocity. So in general, we see that the BRDF is a four-dimensional function, 4 dimensions right here. But for a lot of surfaces, it can be described using a three-dimensional function. These are surfaces that we'll call rotationally symmetric in reflectance. These are also called isotropic surfaces. The easiest way to figure out whether a surface is rotationally symmetric or isotropic is that if you're observing the surface, and you have a surface normal right here, and if you spin the surface around its surface normal, and the brightness of the point that is of interest to you does not change, then you say that it is rotationally symmetric in terms of its reflectance or isotropic. If it does change, it is not isotropic. So here's an example of an isotropic BRDF and an anisotropic BRDF. In the case of the isotropic BRDF, if you take the sphere under the same condition, you don't move its position, but you simply rotate the sphere, the image of the sphere is not going to change. So that's one way to figure out whether it's isotropic or not. Whereas if you take this sphere right here, and if you rotate it, you'll see that its appearance, the brightness distribution, is going to change. The reason this happens is because when you have surfaces that are especially machined, say you have a surface that is sandpapered in one direction, you're going to leave grooves on it which are directional. The grooves are not in all directions equally distributed. There's going to be a preferential direction. In that case, when you rotate the surface around with respect around its surface normal, you're going to see that its appearance actually changes, the brightness actually changes. That's what you're seeing in this particular case. And indeed, in nature, you see that there are lots of materials or surfaces that are anisotropic. It's showing two examples here. Certain butterfly wings, peacock feathers, when you move around, you see that the appearances change dramatically. There are really striking visual effects that are being produced by anisotropic surfaces.